questions of chaos, resonance, and regularity around galaxies. I want to tell you about 3 different papers led by these 3 graduate students. Oh, it's that. It is on. Right. Yes, it is. You can't hear me? Okay, how about that? Is that better? Just talk loud. I thought I was talking loud. Okay, starting again. Physical manifestations of chaos, resonance, and regularity around galaxies. I'm going to tell you about some work by 3 graduate students, 2 of them now postdocs, but ex-graduate students from Columbia, led by those 3. 2 of the papers, Pearson et al. And Price-Whalen et al., already published, and the 3rd one we hope is coming out soon. The basic idea here is that I want to talk about some rather fundamental dynamics and rather abstract dynamics, but try and make it concrete for you. We were inspired to do this work essentially, because of some unexpected morphologies seen in simulations of disrupting satellites that failed to produce thin streams when we expected them to. And so the end point of this talk, after going through some fundamental dynamics, are observable consequences, hence the physical manifestations. And that's why we're having so much fun with this. A connection between fundamental dynamics and observations. So the starting point of this is the paper led by Sarah Pearson. In blue underneath, you're seeing data around the Milky Way galaxy. So these are overdensities in star counts in the halo of the Milky Way. And this is the Palomar 5 globular cluster stream, which is extremely long and thin and spreads over 20 degrees in length and about half a degree in width. The red is a simulation run in a simple potential for a disrupting satellite around a galaxy with a disk and a spherical halo, so in combination an oblate potential. And you can see you can easily make these long, thin streams. On the right is one where we have a particular triaxial model, just one single triaxial model. And you can see in this case, the streams fan out. And it turns out we could not match the morphologies of the Palomar 5 stream in this one model. It's only one model, but the reason this is exciting is this is a very cheap potential measure requiring photometry alone. So it has applications to other galaxies. So in other words, we've ruled out this one potential using morphology alone. Okay, so we wanted to understand why we could not create a thin stream in this particular potential to match the morphology. And the obvious thing we turned to was maybe the orbits are chaotic, and that's why we've got this chaotic-looking stream. Okay, so an aside, let's talk about regularity and chaos so you understand how I'm going to define this. Regular orbits are orbits that have fixed orbital properties. So in a spherical potential, that's the energy and angular momenta. And that means that you have a predictable orbital path. And if you Fourier transform your path in space or in versus time, as a function of time, if you take the Fourier transform as a function of time, whether it's space or velocity, you will find 3 clear fundamental frequencies, represented by omega, which are time independent. So these are also conserved quantities. In chaotic orbits, you see changes in orbital properties over time. They're not conserved. This leads to an unpredictable path, and you should find that these frequencies drift with time. So that's what we're going to talk about I'm going to talk about when I say chaos. So the way you can do this, for instance, to find whether you have a chaotic orbit, you look at x versus time, and you take the Fourier transform. So this is just one dimension of position going up and down versus time. You take the Fourier transform. The Fourier transform here is rather messy. There aren't clear frequencies. There aren't 3 clear fundamental frequencies. And so this is a signature of chaos in your orbital path. Okay. However, when we first came across this, we were rather suspicious of this as being an explanation because traditionally people have thought of galaxies, particularly the halos of galaxies, as rather smooth and fairly symmetric, only mildly triaxial, and chaos, and also very dynamically young. The orbital times there can be gigayears, right? So you've only gone around about 10 times. So the idea that you should have something, an effect that's observable due to chaos within a Hubble time in the halo of the galaxy, frankly, is ridiculous from a dynamical standpoint, right? Which is great. So we did this ridiculous experiment just for fun. And this is what Adrian did in his paper to follow up what Sarah had found in that one particular potential. So Adrian took a very simple potential, an NFW triaxial no disk. Triaxiality consistent with n-body simulations of cosmological structure formation. And he just integrated a few orbits in it. So this is a very regular orbit, another regular orbit. This is a weakly chaotic orbit that he found that is similar to these, and this is a strongly chaotic orbit. Notice the chaotic timescale. That's the timescale we're taking for the frequencies to drift significantly. Here's the number, 10 to the 5 gigayears. So 1,000 times the age of the universe, and this is 10 times the age of the universe. So very long chaotic timescales. Now, what happens if you put a globular cluster, a set of stars, a little cluster of stars on these orbits, and integrate them for tens of orbital times? So for the regular orbits, you get thin streams. For ones with even mild chaos, you see the streams start fanning out. So this is within tens of orbits, even though the chaotic timescale is much longer, you get streams fanning out. Similarly, I'm going to show you this plot because it's relevant later. If you look in frequency space, this is a difference in frequency from the parent orbit of your stars, particles. And you can see in this case, you don't get any change in that difference in frequency. You get a very nice thin spread in frequencies, which is what you expect for your cluster. The frequencies are conserved. But here you can see signatures of the frequencies not being conserved over this time. And these have been calculated by taking the orbital paths and taking the Fourier transform. So we got hints in Adrian's paper that indeed we're seeing a spreading of streams that seems to be correlate beyond our expectation, which seem to be correlated even in a mildly chaotic regime, meaning that it could be observable and important in somewhere like the halo of a galaxy. So what Tomer Javits has done in the last couple of years is taken a bit of a deeper dive into this. So in case this wasn't abstract and simple enough, we're now going to dive into 2 dimensions, because then we can actually map where chaos is in a potential and ask what's going on, and start actually figuring out how to quantify when this effect will be important or not in the real universe. So here we go. We're diving into 2 dimensions now, and I want to for some of you, maybe it's the first time. For some of you, this may give you, it may make you reminisce about graduate school. This is a Poincaré map. The last time I had used a Poincaré map was as a student in Santa Cruz, so it's really fun making these plots. This is, every point on this represents an orbit, right? So this point represents a circular orbit. This is the value, the x value that orbit has when it crosses the y=0 axis, and this is the vx value that that orbit has when it crosses the y=0 axis. So this is always at the same point because it's a circular orbit. As you look at other orbits, this is a rosette orbit. As it crosses the y=0 axis, it has a variety of vx values, and it eventually fills this torus, right? And if you go to these particular points, you're seeing a particular orbit that has similar pericenter and apocenter to the rosette, but it's a resonant orbit. In this case, there's a match in the frequencies, so you get a closed orbit, and it never fills the rosette, and you only get 3 points around here. Now, if we take the same potential, this is well, it's not a spherical potential, it's a planar, it's circular, we squash it, right? So we're trying to introduce some chaos here and see what happens. And then you get these beautiful pictures, which I'm sure you've seen in Binney and Tremaine. This, again, is a Poincaré map. Instead of looking at a quarter, I'm looking at the whole thing here. This is a resonant orbit. This is what that appears in this space. Here's a resonant orbit, which is slightly more interesting than the simple rosette once you've squashed the potential. But what you should notice, if we zoom in here, is around those resonant orbits, you have these little islands. And these are trapped regions around the resonant orbit, where you find orbits that are similar to the resonant orbit. So this is a trapped orbit that would go in these regions in the Poincare map. This is an orbit that exists in the region between the trapped and the away from the resonances. So these are orbits around the separatrix. This is the separatrix between trapped regions and free regions. And this is a regular orbit that would live away from here. The point here is we have regularity in these regions. We have regularity enforced by trapping between the two. Around the resonance, and in between, you get a change in behavior. So we went and looked at this in a little more detail. OK, here's the arrows now. Oh, that was fun, wasn't it? OK, so if we now look at these orbits in frequency space, so these are the same frequency plots I showed you before. And remember, this is what a cluster of stars around very regular orbits look like. And these are actually in the resonant orbit, the trapped orbit. This is the orbit on the separatrix between the two. And this is the orbit in the untrapped region. So you can see, again, you get very regular behavior in the trapped regions. You get reasonably regular behavior away from the resonances. And when you cross between the two regions, you're getting rather interesting behavior in terms of evolution and frequencies. And these are what those streams look like at the end of the simulation, right? So if we want to go even more abstract, let's talk about penduli. Penduli. And we're going to look, this is in the trapped region, we can look at the frequency as a function of orbital periods. This is, at the resonance, n dot omega is exactly 0. So in the trapped region, what you see is the frequencies changing up and down, and they're oscillating around the exact resonance condition. Okay, and that's like a pendulum oscillating around the condition that is just sitting still at the middle. If we move further up, you can see that the amplitude in the trapped region will get larger and larger as you go further and further from the resonance. So this is something within the separatrix, still trapped. This is an orbit that's no longer trapped. And the key thing to see here, that's like moving from when you're just inside where you get a full swing of a pendulum to when you start circulating or going around. So this is an orbit that's circulating. Key thing to notice here, you get a sudden change in the period of this frequency change, where the period halves when you go across the separatrix. So you get a jump in frequencies as you cross the separatrix. It's not a smooth change. So this is what we think is causing the bizarre morphologies. So you start within the trapped region having very similar frequencies and similar changes in frequencies, so orbits stay together. As you cross the separatrix, that's traditionally where chaos appears, but you can actually see it illustrated specifically in a change in period in the frequency changes here. And at that point, you're going to get a difference in how your orbits evolve, and therefore the morphology that you actually see. Okay, so neighboring orbits out of separatrix you should take away from here. In this mildly squashed potential, have frequency changes of order a few percent. So remember that number, because we're going to talk about timescales, the scales in a minute. And the time scale for this divergence to take place, imagine you put a cluster of stars here on very similar orbits. They would start diverging after about 10 orbital periods. Okay? So if we put this all together now, we've come up with a new name for this. Toma came up with this name, separatrix divergence, because it's not strictly requiring chaos, because we're able to describe it. And we want to go further as to say, why should you care about this abstract dynamics? And the answer is because we should be able to observe some of the consequences of this around the Milky Way and potentially around other galaxies as well. And in order to convince you that it's observable, we need to convince you that the scales are reasonable, the time scale is less than a Hubble time, and there's a finite probability of this actually occurring, because the separatrix surface is infinitely thin, right? Another reason why this should not be interesting. Well, I've already told you that the change in frequency at the separatrix is of order 1%. It turns out that people can easily tell you, the order of difference within a cluster, thank you, a globular cluster of stars in frequencies, once you disrupt it, is of order 1%. So this is of order interesting for things of globular cluster size. And if you get a larger separatrix difference, it could be interesting for larger systems. In terms of time scale, the time scale for those changes in frequency to diverge was of order 10 orbital times, which is the time scale in the halo of the galaxy. And lastly, this again is our Poincare map. And what Tomer has done here is he's actually color-coded how big is this delta separatrix around each of these resonant regions. So you can see many, many resonant regions. So this one is of order 3%. So if you take a dwarf galaxy, smallish dwarf galaxy, and it happened to intersect this region, it has rather a large cross-section here, the thickness and depth of this shows you that it would be affected by this resonance. And these higher order ones, there's more of them, and they would all affect things like globular clusters. All in all, we expect of order 10% of orbit space to be susceptible. So there's a sort of 1 in 10 chance, if you put something on a random orbit in this particular potential, that it would be affected by this effect. So, but again, I should admit this is 2D. We're setting up the machinery to understand how to do this in 3D. Now, lastly, I promised you observable consequences. And this is kind of my favorite part. Here's a beautiful map from Cecilia Matteau, who has put together a diagram. This is galactic L and galactic B. And these are all around the Milky Way. So this is, you can look at Cecilia's webpage, and you've got a Python package you can download if you want to know the coordinates of all the streams that have been observed around the Milky Way. So here's the Sagittarius dwarf stream, for example. But notice all these other ones. These are very thin streams. These are all globular cluster streams. They're all long and thin. And here is some real data from Sloan, Sagittarius, the Orphan stream, Palomar 5, the GD1 stream. The point is now, when you look at a map of this, or when I see a map of this now, I actually think of this as a Poincare map of the Milky Way. Or in other words, I can point at this, I can say, okay, this must be a very regular orbit. This must be a very regular orbit on the grand scheme of things. In a way, you're actually doing potential constraints by eye. Any potential you want for the Milky Way has to be able to reproduce these thin streams. So in that way, I think this is what I'm trying to say. I've just spent 20 minutes talking about abstract dynamics, but this is actually giving us a tool to look up the sky and do the sort of experiments that at least I did in graduate school with observations, which to me is really fun. So here's a summary. I think this could be a very cheap potential indicator. Remember, this is morphology alone. We could potentially use this in other galaxies as well. I enjoy this because it's a novel dynamical regime when we're talking about chaotic effects. This is a regime over a few orbits, tens of orbits. It's not like the solar system where we're talking about millions of orbits. You're also talking about specifically about chaos that's manifests when it's not phase average, because you're looking at systems that have not fully phase mixed, streams, etc. And you're looking at ensemble properties, not averaged over many orbits. And it's projected to the observable regime. And I talked specifically about globular clusters, but stellar ensembles come in many different sizes. Dwarf galaxies, globular clusters, they go all the way down to binary stars. So okay, this may not be interesting for other galaxies. For the Milky Way, it's very interesting because we have spectacular catalogs of binary stars coming out. And we can actually look, for example, at the frequencies of binary stars along different orbits and actually think about maybe categorizing individual orbits in the Milky Way according to the degree of chaos that they experience. That's it. Thank you.
Let's see. So you said that the mere existence of thin streams is constrained because you can look at how many of the streams are thin and how many of the streams are thick. So how constrained
Yeah, so I think this is sort of like an orbit map. So I don't think it's as constraining as being able to get the full 60 information along a stream. I think it's more, would be useful as a first order cut to rule out classes of potentials. And then you could restrict your attention to certain potentials which don't have chaotic orbits in these regimes. So it's not as constraining as actually getting the full 60 information. Yes, no, you are completely right. We've got a long way to go. We're in 2D static potentials right now. And so there is a long way to go to understand how this effect fits in with all the effects that you're talking about. But I think the resonance is actually moving. That sounds really fun, doesn't it? So you're right. There is a degree that we have to go. I mean, several degrees. Yep.
Yeah, related to that, I mean, when I was in high school, I learned about chem theory.
Mm-hmm.
Chem theory tells us that you may have chaos. Right there. And there you're told that basically these chaotic orbits, they don't evolve on the Apunov timescales. They're basically constrained by the regular islands around them. And so I'm trying to reconcile. You first showed a chaotic or a timescale of 10 to the 5 gigayears, and then later you showed actually it's only 10 orbits. So how was that first timescale calculated, and why is it so different? Do you understand that?
Yes, I think that the classic way of calculating chaos is to look at the very long timescale behavior. And so the very long timescale behavior, the differences that we're seeing could average out over that timescale. So it's sort of like you're measuring a mean drift, but actually there are changes that occur on shorter timescales than the mean drift. And we're also very interested in orbits that are not infinitesimally close, they're actually finitely close, very close but finitely close. So I think that we're looking at this in a slightly different way. In fact, I'm not sure that some dynamicists would even classify what I'm saying, calling chaos, chaos. As I pointed out, when we traced it down, it could be just the jump in frequency of the separatrix, and it's not so much chaos itself. Right? Right. But I think part of this is definitions and what people have been interested in looking at, which is why I tried to point out why it's a different regime than people have looked at before, why it may not have been noticed before.